Okay, I'm glad to announce Amartya's talk on elementary infinity Topoi. Yeah, yes, today we will learn about analogs of techniques that we learned earlier, but in higher categorical setting. So thank you so much for giving this talk. Amartya, please take it away.
Yeah. So yeah, thanks everybody for giving me an opportunity to speak. And so yeah, so as the title suggests, I'll be talking about elementary infinity Topoi or toposes, like whatever way you prefer. So I prefer Topoi, for instance. And so this AT here, AT stands for algebraic topology. So an algebraic topology, elementary infinity Topoi. So there's a lot of algebraic topology. So yeah, just to put things into context, like we have done quite a lot of algebraic topology with the Grothendieck infinity Topoi, but there are a lot of things that are to be done when it comes to elementary infinity Topoi. So there are a few things that we have done, and so before beginning, let me say this: like most of what I am about to talk about is his work by Nima Rasekh. So most work so most of the things that I'll be talking about, main results in algebraic topology that I'll be like, for instance, I'll talk about. So okay, let's see the plan first. So yeah, I'll just talk a bit about just a brief history and motivation, which I bet like everyone knows, but still I'll just go through a bit of it. Just for completeness, then I'll define what an elementary infinity topos is. So I'd either call an elementary infinity topos E infinity T or a EH T, where H stands for higher. So anyways, and then we'll talk about some algebraic topology in elementary infinity topos. So I'll talk about truncations, how you can think of truncations in an arbitrary elementary infinity topos, and the Blackus-Massey theorem in an elementary infinity topos, right? So, okay, so let's begin. So yeah, as I said, I'll first talk a bit about history, give a bit of a historical context and some motivation, right? So yeah, as I said in the beginning, so it's like mostly, so elementary infinity topos, so it actually can be traced back to works of Shulman, Mike Shulman. And then there's also been a lot of work that's been done by Nima Rasekh. So like my version, like what I will be talking about, so that is work by Nima Rasekh, right? So there are different formulations of elementary infinity topoi that exist. So we'll be seeing the one due to Nima, right? Right. So a bit about topos theory. I don't know what to say. So okay, topos theory, like a bit of kind of historical context, as I said. So it began with the works of Grothendieck, right, or Maki, rather, to study algebraic geometry. So they introduced Grothendieck topoi, right, as a category of sheaves, right. So then, when it comes to elementary topoi actually came later, due to Lavier and Tierney. So yeah. Lavier, so just got to know that Lavier passed away recently. So yeah. So Lavier and Tierney realized that so after some work with the Grothendieck topos, they can make it into something that is suitable for logic, right? So, like very roughly speaking. I would say much. So they introduced the notion of a subobject classifier, about which we will see what a subobject classifier is, which I think you already have seen, I guess. But yeah, I'll still talk about it. And the infinity one categorical history of topos theory. So yeah, let me say this in the beginning. So I'll interchangeably say infinity and infinity one. So when I say an elementary infinity one topos, I mean an elementary infinity one topos, right? Yeah. So yeah, so the infinity higher categorical history of topos theory, it starts with Lurie in derived algebraic geometry notes. So that so that led him to define what we know Grotnik infinity topoi, so which we just call infinity topoi. Then Charles Resk contemporarily invented moral topoi, right, to understand the phenomena of descent. And yeah, there have been other developments as well, but yes, okay. So, and then, so we are interested in a higher categorical and a lot of elementary topoi. So that so the motivation is like it should be, so this category that we want the category of higher elementary topoi or elementary higher topoi, it should be like a category, higher category of spaces, right? And so yeah, as I said, we can trace back it to the works of Shulman and with other with a lot of work by Rasekh as well. So okay. So we'll begin by just talking a bit about sub-object classifiers. So just maybe recall, because this is something that you have presumably seen before. So right, so I bet we have seen this in previous talks by Dubey. So, but in any case, so a sub-object classifier. A sub-object classifier. If there's anything that you don't understand, I'm writing, please make me know, because my handwriting is not that good. Is an object meta and mono, that is a monomorphism. So okay, let me call it T. Such as the initial object, such that for all monos of form. So okay, maybe Z X M. Okay, so I'm working in category C. So C, there exists a unique morphism, which we typically call I believe, yeah, whatever. So okay, let me try this. So this is a picture that you should have in your mind, just to recall. Start. So, right. So we call this. Okay, so an elementary topos, then you, so okay, just recall. So recall again. So just to make sure. For decent plan. So an elementary topos. So when I say an elementary topos, it's an elementary one topos, to be more precise, is locally Cartesian closed category. So this is my acronym that I'll be using. So I'll be using this frequently, I believe. Locally Cartesian closed. So it's a locally Cartesian closed category equipped with a sub-object classifier. We also have general, like more general things, like we have universes and everything. So we'll see that in a moment. All right. So okay, so as so I've not said this. So as Grotnik topoi are like kinds of elementary topoi. So similarly, Grotnik infinity topoi are also special cases of an elementary infinity topoi, right? So okay, so let me define it. So I'm not sure. So there are many ways of defining Grotnik infinity one topoi. So this is the way I'll define it. So infinity one category Z is Grotnik topos if there exists a small category X and an adjunction. Adjunction of this form. So okay, we'll call this L. And this one I, where L is left exact. So L is left exact, and I is fully faithful. Right. So there is okay. So we have this. So the natural way to think about moving from this elementary one topos to an elementary higher topos is to think about some sort of a infinity categorical version of the sub-object classifier, right? So this is basically a locally conditioned proposed category with a sub-object classifier. So that's what we do, right? So that would be the first step. So that will be the first step.
So let me just ask a question. So you say that an infinity category is a gross-index topos if basically it can be represented as a reflexive localization of a pushy.
Yeah, that's right. Yeah, that is right. Precisely.
Yeah. Okay.
Yeah. So it's exactly. So that, as I said, yeah, this is just yeah.
But can we also describe it in a more like traditional way as some kind of a localization with respect to a shift condition?
You can do that. So I think this Luri does it in terms of so it is like a presentable infinity one category, as you said, like where this L that you have, right? So that is left exact. So in the traditional sense, you mean, right? So well, as some sort of a localization, right? So yes, I think so, but yeah, this is the picture that I have in my mind. I think of it. So there's a presentable infinity category with some conditions on it. But yeah.
So I guess my question is, what is the higher version of Giraud's theorem? So how can we recover an infinity site from such a presentation?
Higher version of Giraud's theorem, right?
Yeah, but maybe it's somehow trivial. I don't know.
Yeah, we can talk more about this, I guess. But
Okay.
yeah, there's a way actually. There's a way you can do it. So when you say that it is a growth-making infinity topos, so first it's a locally presentable infinity one category, where there is a version of Giraud's theorems actually, but yeah, so because we're moving from one categories to infinity categories, there's a lot of things that need to be done. But yeah, we can maybe talk about this later if you want, if you're okay for that.
Yeah, sure.
So I actually so this is something. This actually I worked on semantics of homotopy type theory, non-presentable semantics of homotopy type theory previous year, and so this is something that I was kind of So I also asked myself this question. Yeah, okay, we can talk about this later. So so we are kind of thinking of some sort of a higher categorical version of the sub-object classifier, right? So for that I need to define a few things, right? So set as an infinity category. So this is my category of infinity categories with finite limits and pole limits. Finite, pole limits, then the goal limits in Z set to be reversal. Again, this is like all basic stuff, but I'm kind of defining it to put things into context to maybe recall. Set to be universal if the pullback of a coordinate diagram is a coordinate diagram. So what do I mean by that? So it is like stability and the pullbacks, right? So Let me draw this. So, wait, let me make sure that go to my notation. Okay. Anyways, so. Okay. So when I say it is a pullback of a codified is also a pullback. So okay, so you have this F, of course, that was from it to be. Oh, sorry, F. So I've already used A. So right, so that basically means that universality also good, I guess. Okay, so an important lemma. So if Z is locally Z an infinity category Z is locally Cartesian closed with finite limits, then co-limits and Z are universal. Right, so the idea, if I prove it, I think that's not prove it, but the idea is to like so this follows because the left adjoint that so it commutes with co-limits. So that's the idea. So okay, so define so I'll introduce some notation that we'll be using for defining complete SQL universes. So we'll define everything. So yeah, I'll talk about two different versions. So two characterizations of elementary infinity. One of them would be more useful. So one of them would involve complete SQL universes. So yeah, we'll get to that. Okay, so notation. So Z is an infinity category with finite limits. So this is the infinity one category of morphisms in Z. Sorry. So you have this Cartesian vibration. This is a target. And then you have a subcategory of this arrow category. Those objects are the same, but morphisms are the pullback squares. Morphisms are pullback squares. Right, so and there's further another subcategory is the subcategory of subset with objects being the moments. Right. So can you maybe just remark that on So the Cartesian vibration is a subcategory. So this classifies the functor. So what I mean by that, so it's like you take an object and so similarly you have like these 3 levels, we have defined 3 categories. So this is also is another restriction functor that you have. So this classifies the functor. Sorry, that 2 spaces. So it's my category of spaces. So the core and
sorry, can you explain once more what is the definition of OZ?
OZ is a subcategory of the arrow category whose morphisms are the pullback squares, right? As simple as that. So you're just taking the pullback squares. So arrow category is the category of infinity one category of morphisms, and for this OZ, so you just take the pullback squares as the morphisms. The objects were like the subcategory of the morphisms are pullback squares.
I see.
Right? And this is so this I don't know, so maybe just call it the embedded category or whatever. So the embedded, so this is the notation that is used actually. So this category, so this is further, this is the subcategory of the OZ where the objects are the monomorphisms, right? So and you have the same morphisms. So we'll see in a moment. We'll see how these will help us defining so in a way classify, so giving us a universal fibration for objects, right? So that will give us a way of thinking about sub-object classifiers in infinity one categories. So similarly, this functor, so this map classifies the functor instead of sets. So it takes X to sub X. So this is basically the set of isomorphism classes of sub-objects of X, which is a set, right? Okay. So, right. So now we are in a position to define a sub-object classifier. So again, Z is an infinity category with finite limits. So a sub-object classifier of so maybe this so omega is an object that classifies this category that you have embedded category. So think about it. So in this category, the objects that you have, the objects are just the monomorphisms, right? The monic maps, and morphisms that you have at the pullback squares. So the way we had defined a sub-object classifier, it should be quite obvious, I mean, obvious choice. But we'll see that it works pretty well. So this is the definition of sub-object classifier, and then sorry, it should. Yeah, in a category. Okay, yeah, I can say a category. Right. So you have these monos, right? These are like both of them are monos, and this is a pullback square. So that is the deal. So right, that classifier. So another way to think about it is okay, maybe should be clear, but still again. So this is right. So okay. So now so this in a way is like representing this category, right? Now if we want to do the same with this category OZ, right? So just one object doesn't work because it's too big a category, right? So it doesn't work. So just a sub-object classifier doesn't work. For OZ, the thing is that we need a class of representative objects instead of just one object. So we'll have more general notions we'll see. So for OZ, right? So okay. So let me define. So set is equals to, so this is my category. So this is basically, so this means the category of -1 truncated objects of this category, right? So suppose this category, I call it universal. So it's universes, we'll see objects called things called universes. So the objects of this category are objects are these universal vibrations. I'm sorry. Yes. Such that the target is a universe. Okay, so universe, there are many different ways of looking at what a universe is. So I'll just say one way that I think about it. So the rough way of thinking what a universe is. So in a category, okay, so you have this category C. Right. So you have this category C, and okay, you have this category C, and so an object. So universe is like an object classifier. So it is like an object, say, so generally denoted by U, such that so in all the morphisms that you have like of this form, so these correspond, by the way, uniquely to a space of morphisms over X. Right. So that is the idea. So that's why it's like an object classifier. So this corresponds to a space of morphisms over X with local Cartesian closure. So that is what I mean. So I think you have seen universes before, or I'm sorry if you have not. But yeah, this is the idea. This is what I mean. I say universe, but yeah, there are other ways of looking at universes as well. So universe is like an object classifier, and so that gives us a way of working this OZ category. Okay, so now you have a few things that we'll need in our definition of an elementary infinity topos. Okay, so again, you take an infinity category Z. So it is said to have sufficient universes if there exists an equivalence of the following form. So U is a universe. So remember this P that this is like the this is the universal vibration. So this is So I mean, how do you think about it? So this is the way to think about it is like, okay, let me just bring out this. So the way to think about it is that every morphisms this form. So a morphism is an object of a full subcategory of right. So yeah, this is what I mean. Okay, so moving on. Another thing. So now I'll say we'll see how we define closure of universes. So our universe, so from now, like just say I'll just talk about universes, assuming that all these. So yeah, Z as the infinity category, and this is like all these OZ categories and stuff. I'll just say universe. So universe is closed, and so under the property of having finite limits of colimits, and the property of being locally Cartesian closed. So there is locally Cartesian closeness if this category is. And so this is also when I say universe U is closed under having finite colimits, so which means this category is right. So that is terminology that I'm defining, and yeah. So now, okay, now we are finally in a position to define complete Siegel universes. So I will not talk about complete Siegel space or something, or any other different modes of infinity one categories, because that will be a talk on its own. So I'll try to define it in a way that you don't have to know anything apart from this. Yeah. So yeah, just to make sure. So this is a theorem due to Rasekh. So again, okay. So Z, okay, let me write this. So Z is infinity category, and it is a finite complete. And you have a locally Cartesian closed universe. There exists a simplicial object such that things equivalences, and there exists an equivalence okay, so this is like so this may seem kind of odd the way we define this arrow category. So this is just, so by this I just made the subcategory of the arrow category with objects right. So, and okay, so we also have these equivalences. So let me write these down. Okay. So what do I mean by this? So this is like so the way we had defined the universal vibration. So this would be a map of the following form. And then you define M to be sorry. Right. So this simplicial object is a complete Siegel universe. So this complete Siegel universe. Okay, so yeah, so finally there, like now we can define an elementary invariant topos. And then we'll see how there's also a characterization in terms of Siegel, complete Siegel universes. Of course, I won't prove it, but yeah, I'll just give a characterization. So first, coming to the definition, the way we think about it. So again, Z is an infinity category. So then with finite limits and colimits. So Z is an elementary infinity topos. Okay. Z is locally Cartesian closed. So it has a sub-object classifier, but that's not it. So there's another condition that we have. It has sufficient universals which are closed under, again, so as we saw, what does the closure of universes mean? Under finite limits and co-limits. And locally Cartesian closed. So yeah, I've not talked about elementary infinity topos in context of homotopy type theory, which I can do maybe towards the end. So okay, so now here's a characterization. Again, this is like a theorem. So this is a characterization of elementary infinity topos by complete Siegel universes. So this is a, yeah. Okay, so an infinity category is again, so Z, okay. So So Z with finite limits and co-limits is an elementary infinity topology. It has a sub-object classifier and it has sufficient complete C universes closed under same closures that we have finite limits and co-limits and local voltage closed. Right. So okay, now let's see a few examples. So as we saw, so it's a Grothendieck infinity topology, kinds of elementary infinity topology. So example would be so every Grothendieck infinity topos is an elementary infinity topos. Right. And so the category of spaces as well would be an elementary. So we have called it S. So, and another example. So okay, this is okay. Let me say this because this came to my mind. So yeah, I won't explain this or anything. So if you know this, it's good. But so the filter quotient of an elementary infinity topos is also an elementary infinity topos. So this is a way of getting elementary infinity topos. Like so, this is work by Rasekh again. So the filter quotient. So yeah, I won't talk about this. The quotient of so the references would be the elephant, if you want, like the elephant, or a theory of filter quotient of one topoi, and the generalization for the generalization there's actually a paper by, as I said, filter quotient of an elementary infinity topoi, and then there's also okay. So there are also other. So we actually we don't know as many elementary infinity topoi as we would like to. So now just to add this a bit, so there are topoi which again I won't get into the details. We have these realizability topoi, which are examples of elementary topoi which are not Grothendieck topoi. So when I say realizability topoi, so we have so this is so yeah, I don't want to get into the details. So there are different flavors of realizability that you have, but okay, let me not get into it. So there's a one categorical version, like there are elementary one topoi. So there's actually, yeah, there is, and this is something that people have been speculating that there should be a higher categorical version of such realizability topoi. So that would give us like a lot of examples of elementary infinity topoi that are not Grothendieck infinity topoi, and that actually is currently a work in progress. So so I've just said introduced complete sequential universes are like out of nowhere, out of thin air. So okay, so let me say this. So it actually so I'm not sure. Okay. So yeah, you can maybe point out if there's a mistake. So it allows us to, so using complete sequential universes, we you need a lemma for representable Cartesian federations. So for representable Cartesian federations again, so one, okay. Two. So this is I hope this seems, yeah, it seems to. Yeah, okay. So, right now, okay, finally, let's think of, so now So, okay, let me say a word or two. So initially the motivation actually of thinking about elementary infinity topoi was, the motivation came from the semantics of homotopy type theory, actually, primarily, right? There were other motivations as well, but it was a primary motivation. So it was conjectured that, so it was conjectured by Steve Audi. I mean, so this is one of the way you can think about it being, being coming into existence. I mean, so this see, for me is the most important thing for which we needed elementary. Don't worry, but like there are many others things as well. So there was a conjecture Audi that the category of semantics of homotopy type has an initial object, so by work of by some revolutionary work by Shulman, so we understood that homotopy type theory is an internal language for reasoning in the Grothendieck infinity topos. So that was a big deal actually, and recently this problem. So then people started working on it again for an elementary infinity topos model, right? And so there were different like versions of the definitions being proposed, but this definition by Shulman and further characterizations by Rasekh. So this turned out to be right model, and so there's a preprint that you can find. So this has been recently settled by Cherradi. So that now we know that. So there exists an elementary infinity topos semantics of homotopy type theory, but yeah, I'm not talking about homotopy type theory at all. So okay, let's not get into that. So this was some sort of a motivation that I had. Right. So now algebraic topology and elementary infinity topos, right? So why should the topologist care as a part of the title, right? So it turns out this again, as I said, this is something that people have not worked a lot on. I mean, this is something that is quite young in a way, because there are still things that we don't understand in Grothendieck infinity topology, right? Let alone elementary version, right? So for that, so I'll talk about two things. Yeah, so there are other things as well, but I'll just talk about truncations, how you think about truncations in an elementary infinity topos. Again, this is work by Rasekh, and I'll just give a version of the Black-Level's massive theorem in elementary infinity topos. So yeah, so that is the second part or the remaining part of the talk. Okay, so for truncations, we would need to define a natural numbers object. So I'm not sure if you know what a natural numbers object is. So let me go ahead and define it. So in an infinity one category, so most of these definitions and stuff that you have, so the canonical reference would be Lurie's higher topos theory. So in an infinity one category Z, a triple. So okay, let me call it something. Is called a natural number object. So this is the acronym that I'll use, natural numbers object. Natural number object if it is initial among such tuples. So okay, so let me draw this. So by drawing this is the best way to picture it. So initial, okay. So this is lateral pentagon kind of a picture. Okay. So this. So okay. So when I say initial, so let's consider we have another map. So when I say it is initial. So okay, so this is our lambda and this is our lambda dash. Okay, so let's call it F and F dash. So there exists this. Right, so this is what I mean by a natural numbers object. So an important theorem again. This is need to Rasekh. Every elementary topos. So in case of one topo, every elementary one topos does not have a natural number object, but turns out every elementary infinity topos has a natural numbers object. So now, okay. So for the defining truncations, now we'll look at the internal sequential coordinates using a natural numbers object. Okay. So a bit of machinery, a bit of definitions, some definitions that I need to define. So a sequence of objects. So what is a sequence of objects? When I say a sequence of objects, it is like sequence of objects. So it is like a map. Again, so I'm just saying a universal, as I said, so I've already defined the context. So when I say a sequence like this, also that just means a map of this form. And okay, so for instance, okay, so another minor thing that it's worth defining. Okay. So for an object, so suppose you have this object and you have this map. So you can write the resulting sequences. Now, okay. So now suppose Xn is a sequence of objects. Then we can define the internal coproduct. Internal coproduct. So okay. As the pullback. So there's a reason I'm saying internal, so you can see. Right. So it's the pullback. Right. Okay. So now I've defined the internal. Now we can define a sequential diagram. So diagram of sequences. Okay, so sequence of diagrams. So this is the notation. This is a map. Okay, it's a sequence of objects first. So that basically means that you have this sequence of maps. Right, and a choice of maps. So okay, for that, okay, draw this again. A choice of maps should be clear. So you represent a sequence of diagrams as follows. You can just write it like this. Right. And okay, so now we can define a sequential limit or a sequential diagram of objects. The sequential limit, so of J is sorry. So that is the co-equalizer. this is the entity. So yeah, so now we can construct some truncations using these sequential coordinates. And we'll see. Truncations. So we know truncation of spaces, right? So I hope I don't need to get to that. So for an infinity category, Z, X in Z is n truncated. So this category is an truncated space. So okay, an truncated space would mean that so K is untruncated if all these homotopy groups above n vanish. So in fact, okay, so in fact for all spaces we actually have a universal construction of untruncated objects. So we have this adjunction. So this is an embedding. Let's see how this truncation. So okay, so now we are in a position to define truncations. Truncations in an elementary infinity topos. So this is also due to Rasekh. For an elementary infinity topos Z, we have an adjunction. Right, so yeah, so now as promised, so I'll state this version. So this is the last thing that I'll be saying, last thing that I'll be saying. So this is the Black-Macy theorem. And then elementary infinity topos. So I'll just write the theorem onto it. Rasekh again. So suppose, and then elementary infinity topos Z, we have a push out diagram. So notations, right? Such that K is M connected, K dash is N connected, and then if this one C is a person connected. Right, so yeah, there are also, as I said in the beginning, a lot of things that we don't know. Like one of them that comes to my mind is like, so we don't know if we have a notion of an Eisenberg MacLean object in elementary infinity topos, then like further lines, further things in direction. So because we can get the food impulse suspension theorem from this, from Black-Macy theorem classically, so we'd be interested in the other things, like so there's a lot that needs to be done right now actually, and yeah, there are things that we don't understand even in context of elementary infinity topo, in Coordinate infinity topo. So this is something that is quite active actually, and now like for instance, now most of the work that we are seeing in this direction, so a lot of it, as I said before, comes from Rasekh and other people from the Homotopy Type Theory community, but like most of what I talked today is due to Rasekh. So yeah, so that is where the most most of the work's been coming from in the recent years. And as I said, right, so maybe I can say a bit about what I was about to say then. So yeah, now there's been like further interest. So there's this interesting thing that something that I've been thinking about. So we know that so due to I'm sorry, I don't remember the names of all this, but so it's been proven that we can have Heisenberg Maxwell objects in homotopy type theory, right? And now after this groundbreaking work by Shulman and Cherradi and Rasekh, that by Cherradi to be more specific, for having an elementary infinity topos model of homotopy type theory. So it seems that we indeed would have a notion of an Heisenberg Maxwell object in an elementary infinity topos, and there's a possibility for a lot of other stuff as well, but yeah, so there's a lot that needs to be done in that direction. So okay, yeah, I'd like to say that's it. Let's stop. Thanks for listening.
Okay. Thank you. Should I stop the recording? Or
yeah, if somebody wants to, if there's something that one wants to talk about, then we can chat, or maybe we can stop recording.